Hi everyone, I'm Nguyen, a professor from Southeast University in China. I'm going to present Imma Sort by two or more attributes with interpretable monotonic multi-attribute sorting. This work is supervised by Prof. Brian Lin from National University of Singapore when I was a postdoc researcher there. Imagine you're traveling to a new city and you choose one hotel from a set of hotels. You are interested in two criteria: the distance to downtown and the price per night. Sorting by distance may help you choose a hotel that is not far from downtown. Sorting by price may help you choose a hotel with an acceptable price you are willing to pay. What we learn from simple sorting is that the monotonic increasing or decreasing trend provides an intuitive base for comparison. It is easy to anticipate the attribute values of an item in the list. For example, you can easily select the top 4 hotels with the lowest price. But what about the other attributes? When you look at the distance, you will find the distance are in random order, and the top 4 hotels you are interested are too far away. Then, you may want to sort by distance. That gives you a totally different order. You will find that the top few hotels are close but quite expensive. Then you get lost to your previously interested hotels. You may want to switch back to the older list and keep searching. Such search experience is quite struggling, and that motivates us to ask a question: why can't we have both attributes sorted at the same time? Well, I'm going to sort by 2 more attributes with interpretable monotonic multi-attribute sorting. Let's try to resort this list of hotels. We can relax the monotonicity for price. Then distance becomes more monotonic. If we keep relaxing price further, distance becomes strictly decreasing. Alternatively, if we relax the monotonicity for distance, price becomes more monotonic again. Well, we can stop at such intermediate state where both attributes are approximately monotonic. Don't you think such a sorting is more interpretable than a single sorting? Yes. In this sorting, users can easily perceive the increasing or decreasing trends of both attributes. So, as the trends can be intuitive and helpful for decision making, we could trade off such monotonicity in the first sorted attribute to improve the trend perception of other attributes. Now, this raises research questions. How to balance the monotonicity? Can user actually understand it? Can users search such lists? Firstly, let's answer the first question: how to balance monotonicity? Suppose we consider 2 attributes and need to sort 3 data items A, B, and C. If we sort by attribute 1, we have the order of A, B, C. In this case, attribute 1 is monotonic, but attribute 2 is not. Similarly, if we sort by attribute 2, we have the order of A, C, B. In this case, attribute 2 is monotonic, but attribute 1 is not. This is because the 2 attributes are not perfectly correlated, which is very common in real-world data. That makes the 2 attributes cannot be monotonic at the same time. Therefore, we turn to looking for perturbations of data attributes, such that the perturbed attributes can be monotonic at the same time. For example, the perturbed A', B', C' are monotonic in both attributes. Also, different perturbations can have a different monotonic order. Then, how to find such monotonic perturbations? One simple way is to fit data points onto a monotonic line. Their projections on the line is monotonic. We can sort the data points by their projection sequence along the line. For example, this order should be A, B, C. There could be numerous lines help with such sorting. We should find one that minimizes the total perturbation. That is, the total distance from each data point to its projection. However, Monotonic straight lines may not be able to fit arbitrarily distributed data points very well. Instead of fitting to a line, we adopt monotonic cubic Bayesian curve to fit data points. Similarly, we choose a Bayesian curve that minimizes the total distance from real data points to their projections. We also use a weighted distance, for example, W1 and W2, to control the monotonic smoothness of each attribute. If we set a higher weight on attribute 1, then attribute 1 could be more monotonic than attribute 2. Let's see how to sort this list of hotels. Firstly, we normalize the distance and price into a range from 0 to 1. Then, fitting those data points with a Bayesian curve by minimizing the total weighted distance. The hotels are then ordered as the sequence of projected data points along this curve. If we plot the perturbed price and distance, you can see both price and distance are strictly monotonic. Let's see the actual price and distance. You can see the actual price is approximately increasing, and the actual distance is approximately decreasing. Let's see how to use Imma Sort. Imagine we need to select the cereal from a list, and we care about nutrition attributes including fiber, protein, and carbohydrates. A common way is to sort by a utility of weighted sum of attributes. We usually start searching from the first one, which has the highest utility. However, when I look at the first one, I realize I may want high fiber. Then, I need to search down for high fiber. I search down, but also realize that this item has much lower protein, which makes me jump around to compare these alternatives for a while. Finally, I may choose one. Let's see what will happen if I use Imma Sort. In this sorting, I can see fiber and carbohydrate is decreasing, while protein is increasing. Imma also highlights the cereal with the highest utility, so I can directly jump to the highlighted one. What if I prefer high fiber? I can look upward and see the increasing fiber and carbohydrates but decreasing protein. I can easily compare adjacent or nearby items and then quickly choose one that compromises lower protein with high fiber. Comparing with Sort, Imma Sort supports much more intuitive search, allowing easy comparison, thus improving the sorted list user experience. These are mockups of list user interfaces using Imma Sort. By sliding left and right, users can perceive monotonic trends and make easy choice on food dishes and movies. We had 3 types of evaluations. Firstly, we run characterization simulations to study when and how much Imma Sort improves the ease of prediction. Then, we conducted quantitative user study to examine user performance in prediction and search tasks. Finally, we conducted think-aloud interviews to understand usability, usefulness, and interpretability of Imma Sort. We had compared 3 Imma Sort variants with baseline sorting method. The first Imma variance that purely sort items that all attributes are approximately monotonic. The second one called ImmaAnchor that highlights the best item in the list. Sometimes the anchor item may be ranked behind. The third one, ImmaCenter, that directly put the highlighted best item in the center of the list, so user can search from the center. The baseline sorting methods include simple additive weighting, sort by the first attribute that has a higher weight, and sort by the second attribute that has lower weight. In our characterization simulation, we found that Imma Sort provides the best predictive interpretability among techniques across the factors of various attribute correlation, list length, and attribute number. In our quantitative user study, we had 2 tasks. In the prediction task, participants were asked to predict the last attribute value given a list. Participants found that Imma Sort improved the ease prediction accuracy and confidence compared with Sort and by A2, but less predictable than by A1, in which the attribute is strictly monotonic. In such task, participants were asked to select the best item from a sorted list. We found that ImmaCenter supports the best search performance and satisfaction and is rated helpful. In our qualitative think-aloud interviews, we found that using Sort, participants has difficulty comparing items. By highlighting the best item in a single attribute sorting, participants can quickly navigate to the anchor, then compare nearby items, but they have difficulty compare unsorted attribute values. So, participants preferred ImmaAnchor as they appreciate monotonic trends in all attributes. They even appreciate more if the anchor is placed in the middle of the list in the beginning when they start searching. They directly focus on navigation around the anchor. To sum up, we propose Imma Sort to relax the monotonicity requirements in sorting to enable approximate sorting along multiple attributes. We had mock-up demonstrations and usage scenarios for Imma Sort for various consumer decision-making applications. We had characterization simulations to study how well Imma Sort could improve the ease of prediction. We evaluate the learnability, usability, interpretability, and user performance with user studies. We find that Imma Sort improves the interpretability and satisfaction of sorting by 2 or more attributes. Thank you for your kind attention, and I'm happy to take questions.